All right, picking up where we left off in chapter 4, where am I getting this number of valence electrons from? Well, you can draw out the electron configuration if you want, or you can remember that the group number, especially in the AB system, if we use the A system, it's going to be equal to the number of valence electrons. So group 3 has 3, group 4 has 4, group 5 has 5, group 6 has 6, group 7 has 7, and group 8 has 8. That's one of the easier ways to do it. So group 3 likes to form 3 bonds, group 4 likes to form 4 bonds, Group 5 likes to form 3 bonds, Group 6 likes to form 2 bonds, and Group 7 likes to form 1 bond. Now, Group 8, they rarely form bonds unless they're going to be in some type of special compound. Exceptions to the octet rule include electron deficient species, radicals, and expanded octets. So there are quite a few exceptions, but they fall under different categories, and some have more than others. Electron deficient species are those that are okay with less than having 8 electrons. So they're less than having an octet, they're okay with that. Beryllium and boron are those two exceptions that you need to know. So you need to know these. And beryllium is okay with only having 4 electrons, and boron is okay with only having 6. I don't know what to say other than you need to know that. Free radicals. So most of our electrons are always going to come in pairs. So that means they have even numbers of electrons. But some stable compounds do have an odd number of electrons. If they contain at least one unpaired electron, they're going to be called a free radical, and they're usually very reactive and react very rapidly, very quickly to get rid of that lone electron. However, those that are more reactive sometimes are not as bad for the environment or something like that than something that's a little bit less reactive, because it can go higher into the atmosphere and it can do more damage. So if it reacts, before the stratosphere, it may not do as much damage that if it reacts in the stratosphere, it's going to help deplete the ozone layer, things like that. This is why we have to look at NOx emissions, where X is between 2 and 5. And you'll notice a lot of these compounds. So this is NO2 here. This is NO here. So we have some NOx compounds that are going to be problems as they are given off by industry. So when we have an unpaired electron, that's called a free radical. Now for this class, you're going to have to be able to identify a free radical. You might have to talk about it. Why is it a problem? Something like that. But you're not going to have to draw structures that include free radicals. So if your structures have an odd number of electrons, make sure you look back and count. If you have like PO4, 3 minus, so phosphorus has 5, each oxygen has 6, 6 times 4 is 24, plus 3, because we have a 3 negative charge, means we have 3 more electrons. So this would be 32 electrons for the whole structure. So don't forget to add or subtract electrons for the charge on the molecule. Expanded octets. This is where we're going to have the most exceptions. And that's because it's anything period 3 and higher. So anything that's found in period 3 or higher technically can form an exception. There are a lot of elements that will form them more often than others. So atoms are larger once we get to period 3. They can accommodate more than 4 atoms that are close around them, but also they have d orbitals that we can throw those electrons into. So the first thing to do when you're drawing a structure for something that could be an expanded octet, or you think is going to be an expanded octet, is find the total number of valence electrons, just like we always do. Build the skeletal structure, just like we always do. Assign electrons to the terminal atoms until they have an octet, or use the Lewis dot symbol. These are all the same rules we were using before. This is the one that's different. Assign any remaining electrons. Where do I assign them to? All right, if we have no unassigned electrons and the central atom does not have an octet, you'll form a multiple bond. But if you have extra remaining electrons, you'll put them on the central atom usually. Oh, yeah. Put them, not usually, but put them on the central atom. Okay, so that's where we're going to see a little bit of differences 4 and 5. So for example, PF5, 5 valence electrons for phosphorus. Each fluorine has 7. 7 times 5 is 35, gives us a total of 40 electrons. Now, I like to kind of do this still. that we're going to use all of these electrons to form. So we have phosphorus and we have fluorine like this. So we have our one lone electron. So I'm going to try, and I have 5 of these, right? So 1, 2, that was my other one for fluorine, 3, 4, 5. Are there any extra electrons? No, everybody has an octet. And we have used all of the electrons. But phosphorus actually has more than an octet. Phosphorus has 2, 4, 6, 8, 10 electrons, but each fluorine has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So each fluorine has 8 and phosphorus has 10, but we only used a total of 40 electrons. And you could do that by saying, well, if each fluorine has 8, 8 times 5 is 40, or you can actually just count them: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So you have a couple options there. Now, if I have something that's charged, I tend to have a molecule that doesn't have only one structure. There are molecules that are uncharged that have more than one structure as well, but there are going to be some molecules that we just can't represent correctly by one single Lewis dot structure. So if I look at this, what I have right here with the red oxygen having a single bond and a green oxygen having a single bond. If you remember from a few slides ago, this is a group 6. So it really wants to form 2 bonds. Each of these oxygens wants to form 2 bonds. This oxygen has 2 bonds, but these oxygens do not. So what I need to do is put a double bond in there. But does the double bond go here, like in the top structure, or does the double bond go here, like in the bottom structure? And remember, we know a general length and strength for our double bonds, single bonds, and that kind of thing. So when we measure this, we measure the length and the strength, we actually find out that it's neither. It's actually somewhere in between a single bond and a double bond. So neither is correct. So what we would do is we would draw both structures and separate with a double barbed arrow. So I would say, this one, double barbed arrow, means they resonate back and forth between the two structures. So they're called resonance hybrids. And we use that double barbed arrow to draw between them. Sometimes there's 2, sometimes there's 3. You can have multiple different structures. Something like nitrate. So this is nitrate. Has 3 possible structures. So we would have the double bond. Let's draw them in different colors. Here on this oxygen. Or we can have the double bond on this oxygen. Or we could have the double bond on this oxygen. So either way, and I can do that on all the structures here, just make them different colors. Wrong button. because we're going to calculate formal charge for each of these, and I want you to know which one I'm talking about each time. So all right, let's calculate formal charge. And what that means is we're going to compare how many bonds it wants to have, the number of electrons the atom has. It's basically calculating whether we have an electron surplus or not, or an electron deficient species. So for structure number 1, I don't know what just happened, but for structure number 1, so we'll do this one number 1, the oxygen. You can look at this. There's so many different ways to do formal charge, but this always works. But there are easier ways to do it if they follow the octet rule. So you take the number of valence electrons in a free atom. So that meant if I just had a free oxygen, how many valence electrons would it have? It would have 6. So 6 minus 1/2 the bonding electrons. Well, how many bonded? 1, 2. Each of those has 2 electrons, so I'm going to say 1/2 times 4, right? Then I'm going to say minus all of the non-bonding electrons, 2, 4. So I get 6 minus 2 minus 4, or 0 for a formal charge on that one. All right, let's go to the blue one. Oxygen is 6 minus 1/2 of 1, 2. So 6 minus 1/2 of 2 minus 2, 4, 6. So this is 6 minus 1 minus 6, or -1. So this is a -1 formal charge. Then the green one, for another oxygen, is 6 minus 1/2 of 2 minus 2, 4, 6, or 6 minus 1 minus 6 is -1. The formal charge should end up equaling all the charges in the molecules added together. So right, we're at -2, and we know it needs to be -1. So let's do the nitrogen as well. A nitrogen atom would have normally 5 valence electrons. So we would say 5 minus 1/2 of all the bonding electrons, 2, 4, 6, 8, minus 0. So this is 5 minus 4 minus 0, or plus 1. Plus 1. I'm going to get rid of all the excess stuff I don't need here. So nitrogen has a +1, and 2 of the oxygens have a -1, for an overall formal charge on this molecule of -1. And that would be true for each one that has a double bond, would be 0, and the other ones would be -1, because if you think about it this way, oxygen wants to form, try to find a color I haven't used yet. Oxygen wants to form 2 bonds. So oxygen wants 2 bonds. But here it only has 1 bond. So it's -1 bond. So the formal charge is -1. Here, again, -1. And here it has 2 bonds. It wants 2 bonds, so the formal charge is 0. Nitrogen wants to form 3 bonds, but it has 4 bonds, so it has +1 bond, so it would be +1. So that's a quicker way to find the formal charge on things. I'm sure if you look up formal charge on the internet, you will find a whole bunch more ways to calculate it. But just so you know, this way always works. So I would use the formula. So a Lewis structure with no formal charge is always best, or generally best, than a Lewis structure that has formal charge. So if you can, you'll draw one without a formal charge. Small formal charges are better than large formal charges whenever possible, and This one's important that negative formal charges should be on the more electronegative atoms. That means they have more electron density more of the time. So for example, H2CO, we have this possible structure where carbon has a -1 and oxygen has a +1 bond. Or we have this possible structure where carbon has no formal charge and oxygen has no formal charge. So overall, this would be a better structure because of this rule right here. So you're going to need to know these three rules and be able to understand how to apply them and see which structure is going to be best. So which of these two structures would be favored? Here we have nitrogen. We have to calculate the formal charge. Well, they're actually already calculated for you. Nitrogen is +1 because it has 1, 2, 3, 4 bonds and it wants 3. This nitrogen has a 0 formal charge, and oxygen would like 2 bonds, but it has 1, so it's -1 bond. This nitrogen would like to have 3 bonds, but it has 2, so it's -1. This nitrogen would like to have 3, but it has 4, so it's +1. Oxygen would like 2, and it has 2, so it's 0. But in this case, the only thing different really is the electronegativity of nitrogen is 3 and oxygen is 3.5. So whenever possible, oxygen should get the negative the negative formal charge whenever possible. So let's look. Here oxygen has a 0, here oxygen has the negative. So in this case, apparently this isn't working. This one would be correct because it has the negative formal charge on oxygen. It would be preferred. Last one here, I think. Identify the best structure for isocyanate. I want you to go through, pause it, go through, calculate the formal charge for each of the atoms in each of the molecules, and tell me which structure is best. Now, I know carbon's not the central atom here. Carbon will be the central atom when you have to draw a molecule if it's present, but not necessarily in a molecule that I give you. So if you don't pause it, you're missing out. You should pause it and try it. So here are the formal charges. Carbon wants 4 bonds, it has 2, so it's -2. Nitrogen wants 3, it has 4, so it's +1. Oxygen wants 2, and it has 2, so it's 0. Carbon wants 4, has 3, so it's -1. Nitrogen has 4, it wants 3, so it's +1. And oxygen wants 2, it has 1, so it's -1. Carbon wants 4, it has 1, so it's -3. Nitrogen wants 3, it has 4, so it's +1. And oxygen wants 2, it has 3, so it's +1. And again, the formula works for all of these if you want to try that. But anything that follows the octet rule, for sure, this way works as well. So looking at these, the first rule is anything that has no formal charge would be preferred. Well, that's not possible. The second rule, small formal charges are better than large, and then negative formal charges be on the more electronegative atoms. So small is better than large, which really gets rid of this one. But also, if you look, carbon has an electronegativity of 2.5, nitrogen of 3.0, and oxygen of 3.5. So here carbon has a -3 and oxygen has a +1, so this one is definitely not a good structure. Here carbon has -2 and oxygen has 0. Those would want to be switched if possible. So the best structure would be this one because oxygen has the most electronegativity. It would want to have the most negative charge it could have. So B would be the structure that would be preferred. That's it for chapter 4.